vital instrument in many kinds of chemical analysis. But how does it work? And how do we interpret the data that we get from it? A mass spectrometer works in 5 stages. First, the sample is vaporized. Then, it is ionized. Third, it is accelerated. Fourth, it is deflected. And fifth, it is detected. The deflection stage is the heart of the mass spectrometer. When we accelerate an ion, it would like to keep moving in a straight line. This tendency of the particle to move in a straight line, its momentum, is proportional to its mass. However, in a mass spectrometer, we use electromagnets to try to deflect the ions off their path. The amount of force that the ion feels from the electromagnet is proportional to its charge. The path that the ion actually takes is a result of its mass-charge ratio. A different particle with a different mass-charge ratio will take a different path. And this is what we are actually detecting, different mass-charge ratios. So let's analyze a sample. If we vaporize it and ionize it, accelerate it, deflect it, and then detect it, we can record its mass-charge ratio. If we repeat this with more of the same sample, we will record different size fragments. Eventually, we'll know the proportions of all the different size pieces in our original sample. So how do we interpret mass spectrometer data? Let's consider rubidium for an example. Here's some mass spectrometer data from a natural sample of rubidium. It tells us that 70% of this sample of rubidium was the rubidium-85 isotope, while the rest was the rubidium-87 isotope. If we multiply the percentages times their mass and add that up, then average that over 100 atoms, we'll find the average atomic mass of rubidium. Let's try the reverse. Let's calculate the relative abundances of boron-10 and boron-11 isotopes. First, let's imagine we had 100 of these boron atoms. Let's call the number of boron-10 atoms X. Then, the number of boron-11 atoms has to be 100 minus X. We can put this together to calculate the average atomic mass, which we already know for boron if we look at the periodic table. Do a little algebra, and it tells us that X is equal to 19, which is a percentage of boron 10, and therefore boron 11 has an abundance of 81%. That's it. Thank you for watching.